Hello everyone, I'm Jiang Ruiyao. Today I will introduce an Arduino-based water ring liquid level sensor. First, I will talk about the objective. A water-conducting water level sensor was calibrated using an Arduino system to establish a mathematical model relating the sensor's output ADC value to the water level. The calibration was then used to evaluate the sensor's measurement accuracy and applicability in practical applications, such as water tank control, rainwater harvesting, smart irrigation, and flood early warning, providing a basis for water level monitoring systems. And then I will talk about the introductions. Water level monitoring is related to water resource management, agriculture irrigation, and urban flow control. Traditional water level monitoring technologies like ultrasonic, flow type, and capacity sensors offer high accuracies and stability, but are costly and complex to install, making them unsuitable for large-scale or low-cost applications. In recent years, Arduino-based embedded sensing systems have been applied to water quantities monitoring and water level detection environments due to their open-source nature, access of expansion, and low cost. Therefore, low-cost, easily integrated water-conducting water level sensors, and their calibration methods are more suitable. And then I will talk about the theory and sensor principle. The sensor is a water level sensor based on the principle of conductivity, and its structure consists of multiple sets of parallel exposed copper strips on a PCB board. Water conducts the copper strips, forming a conductive path, reducing the resistance across the sensor and changing the output voltage. Arduino reads the voltage through the analog input pin A0 and converts it into an ADC value 0 to 1023. The higher the water level, the more conductive paths are, the larger the ADC value. A relationship between ADC values and actual water levels was established, and calibration was performed using a linear regression method. During calibration, multiple node water level ADC values were recorded, and the fitting formula was ADC equal to AH at B, where H is the water level height minimum, and A and B are calibration consistents. The model is simple, effective, and used for calibrating water conducting sensors in cleaning water bodies. And then is about the experimental setup. The system consists of an Arduino mainboard, a water conducting water level sensor, a transparent cleaner container, a millimeter ruler jumpers, and a breadboard. It operates in a consistent 25-degree environment, using filter tap water to minimize the impact of water quantity fluctuations on conductivity. The sensor is vertical fixed inside the container with the level water starting at 0 and gradually increasing in 20 intervals to 120. 3 ADC values are recorded at each water level point, and the average value is taken to reduce redundant error. Then, this is the data table. At the water level of 0, the average ADC value is 26.7. At the water level resist, the ADC value gradually increases. reaching 582.3 at 180. The data shows an increasing trend, consistent with liner fitting. And then is analyze and the graph. Linear regression analysis of the average ADC value yields the following formula. ADC equal to 4.75H plus 27.2, where H is in millimeters. The coordinates of fits are 2, which is 0.995, indicating good linear response of the sensor within the 0 to 120 range, making it suitable for water level monitoring in this interval. So the graph shows the relationship between water level, the ADC value, the scatter plot response measure data, and the straight lines represent the fitting result. The data points are closely disclosed on both sides of the fitting line, demonstrating the sensor's linear characteristics and the effectiveness of the calibration module. And then about the error analyzing and limitations. The sensor exhibits good linearity, but the limitations, even without water, it outputs an ADC value of 25 to 30 due to zero drops caused by Q fault conductivity and ambient humidity. In shallow water less than 5, the sensor response is unstable and relationship is low because the conductive path changes are not significant. With long-term use, electro-oxidation, water quantity changes, and the temperature fluctuations affect the measurement accuracy. The sensor is suitable for short-term, small error monitoring stationary with stable water quantities. And then about the comparison with literature. Ruiyao and controllers in 2016 research calibrate water conducting sensor to near ultrasonic accuracy. Sheet in 2021 research introduced temperature and conductivity compensation to improve the long-term stability of the sensors. Philips in 2024 research demonstrates the successful application of Arduino systems in hydrological teaching the monitoring. Therefore, this study provides theoretical and methodological support. And then, in conclusion, a linear relationship between ADC and water level was successfully established, and then suitable for educational dimension stress and shallow water monitoring of overtype systems. About the limitations, sensitive to water qualities, electropolations, and affected by temperature. And about the future recommendations, integrate temperature compensation, wireless transmission, and multi-sensor function. So this slide is about the reference. That's all. Thank you.